Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on Common Polymers 101. This is part 5 of a 5-part series we're calling Chase Plastics 101. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. I have a few quick housekeeping items before we get started. If you are watching us on YouTube, we encourage you to like and subscribe so you receive future notifications when Chase the Knowledge webinar recordings are posted. As for those of you who are attending live, everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand using the react icon in the toolbar, and I will unmute you and call on you to ask your question out loud. We will answer all questions at the end of the webinar, so stay tuned. You can access and download PDF copies of this presentation, our product line card, our soft touch one-pager, and information on our technical engineering team in the materials section during the presentation. If you are attending live, a certificate of completion and a recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of the presentation and handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on the products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted. You can register for our next webinar on Introduction to Plastics Additives on December 10th now. You can also watch parts 1 through 4 of the Plastics 101 series, as well as any previous Chase the Knowledge webinars from this page at your leisure. You can subscribe or invite coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars. As I mentioned, we are also on YouTube. Just search for Chase Plastics on YouTube to find our channel where all Chase the Knowledge webinars are and will be posted for easy viewing. Hit subscribe to be notified through YouTube when we post new content. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. In addition to our presenter, Andrea Kendrick, whom I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise that she brings to the table. Without further ado, Andrea.
Hey, good afternoon, everybody. Andrea Kendrick here, going over our last part of our 5-part series. Today, we're going to go over some common polymers. And so, without further ado, let's get into it. Our agenda for today, we're going to do a little bit of review. If you were on for the basics, polymer basics, our first part, we went over the polymer classification a little bit. and we did semi-crystalline versus amorphous as well. So we're going to review that just shortly because it does play into the performance of the materials that I will cover later in this presentation. Then we're going to go over different commodity materials, different engineering materials, different specialty materials, and then lastly, some soft touch materials. Okay, so again, if you were part of the or watched the first part on basics, you'll recognize this pyramid here to go over the different materials. So the different classifications and how I also then broke up this presentation a little bit. You're going to have your commodity grades at your bottom of your pyramid. They're lower cost typically. You're going to see a little bit lower performance. Generally, thermally is the big one there. And then you're going to see that you typically buy them in really large quantities. So typically when you think plastics, these are going to be the materials that are first come to mind, unless you're someone that does in fact just mold a bunch of specialty products. So we'll cover a few of those under the commodity section. Then you have your engineering. So now you're going to go up in cost a little bit. You're going to go up in your performance a little bit. And generally you buy them in moderate quantities. There are some applications, of course, where you might buy a ton of the material, or you might only buy a little bit. But you're starting to see an improvement in some of your performance features here. So a little bit better heat performance. And then they might also have a special or unique value proposition within that material as we're going through it. And then specialty at last is going to be your higher cost materials. They have a special attribute or attributes that make them unique in how they perform. And so there's a couple of them we're going to go over today and talk about those specifically. Higher performance, specifically in heat performance, and then again, also in a unique value or value proposition that make them apt for whatever they're being used in. And generally you buy them in smaller quantities. There's not always as high a demand in some of these specialty applications. So then the material demand is also not as high. Okay, so then again, we're going to review, if you were on the basics, you've seen this. We're going to do a semi-crystalline review quickly and amorphous review quickly. Again, because I talk about the morphology of each material I cover, I want to make sure that we're understanding kind of what that means about the material before we get too far into it. So semi-crystalline materials, they have highly ordered structure. They have crystal regions, and they are semi-crystalline because they're not 100% crystalline. A general rule of thumb is 30 to 70-ish% is a good percentage. So 30% of it might be crystalline versus a 70% depending on which material we're looking at. They are typically opaque. There are some exceptions where we have made some of our semi-crystalline materials clear, but they are typically opaque because the crystal regions do not allow the light through. They have a sharp melting point. So your TM is going to be where you're going to run a little bit hotter than that, because your TM is the thermal point at which those crystal structures will start to break apart. There's enough thermal energy, they'll break apart so we can process them. They tend to shrink more. And so you'll see that across the board as I cover the materials, I also include a broad shrinkage range. And so you'll see that it's going to be typically a wider range, and it's going to be a higher number, a larger value for shrinkage for your semi-crystalline materials compared to your amorphous. Okay, and then they tend to have improved chemical resistance or wear performance. You'll see in some of the materials that I cover, that's going to be some of those value propositions, that they have good chemical resistance or good wear performance. You'll see that pretty commonly with our semi-crystalline materials. Okay, and then amorphous, random structure. A means without, and amorphous is structure. So without structure, it's got a random structure to it. They are typically transparent because they don't have those crystal regions to block the light from getting through. There are some exceptions to that, and we will talk about some of those when we get to some of the materials that I'm going to discuss today. They have a gradual softening temperature. So because they don't have those crystal regions that require that temperature to break them apart, they typically they separate and expand further out past your TG. So they have generally a little bit of a wider processing window thermally than your semi-crystalline materials are going to have. They don't expand as much or have to expand as much when they're being processed. So they therefore turn around and they don't shrink as much either. And so a smaller range, generally in the 3 to 7 thou for your shrinkage there. Again, I have the shrinkage values for materials we'll cover. With that, it does allow for better dimensional stability and tighter tolerance control out of your amorphous materials. So you'll see in a couple of the materials we talk about that will be brought up as a value proposition for it. And then also because it has less likelihood to shrink or shrink non-uniformly, you're less likely to experience warp out of your amorphous materials as well. Okay. All right, so that is covering our general overview and reviewing what we had. Before I get into each of the individual materials under those sections, a couple things I want to point out. One is going to be the generic values that are provided here are just that. They're generic and generally a really good range or point to start with in terms of the performance of the material. I would always advise, if you know you're going to use a very specific grade of this material, use that data sheet, use that value, use that information provided by the manufacturer. So again, keep that in mind. The other thing to point out is I do provide some shrinkage values for these different materials. And so again, that is a general rule of thumb and a good starting point. But also remember, with shrinkage, there's things that will affect it. And so it's not a hard and fast rule that that's the exact value. So if you have stuff like, if you're going to have multiple gates on your part, if you're going to process it different than normal, the location of your gate, all of that can affect the shrinkage. So just keep that in mind when you see those values. And then the last note is going to be, I will talk about TPEs briefly, and I will also talk about nylon as a family of materials. But do note that there are webinars that already exist covering those two topics. So if you're interested or you're using those materials and you want more information, those webinars do already exist. So feel free to go and find those, or shoot me a note afterwards and say, hey, I want to review that or listen to that webinar, and I'd be happy to help. Okay. All right, so we're going to start with commodities. I cover a few of the commodities. I'm not covering all of them that are on the pyramid. So if there's a certain commodity you have questions about or would like to know about, same with the engineering materials and the specialty materials. I could talk for hours on end, and I'm not trying to take up all of your time doing that. So if there's a commodity or specialty or any material really that's not covered and you want to talk about it, feel free, get with me and we can talk about it. But the ones that I do cover, we're going to start with polypropylene. So morphology, it is a semi-crystalline material. So we covered that, means you're going to have a little bit more shrinkage. So the shrink for your propylene is in the 1.7 to 2.2 range, or 17 to 22 thou range. Your specific gravity, generally unfilled, is going to be about 0.9 to 0.91. Because it is lower than 1, which we compare it to water, these materials will float. So if you've ever worked with a propylene part or pellets, if they're unfilled, pellets will float or parts made of it will float. So melt temperature, also this table, by the way, is going to be provided for all of the materials that I cover. So it'll be a nice quick comparison if you want to jump through slides after the fact to compare your values. So melt temperature for propylene is going to be between 400 and 450, and your mole temperature is going to be anywhere between 60 to 120. Okay. I also provide the chemical structure for most of the materials that we're going to cover. So you can see your propylene here is pretty simplistic, just a hydrocarbon molecule or material, I should say. And so you can see it just has the CH3 off the backbone. That's the only thing that makes it unique from ethylene, which we will also see later. Okay, so some information about polypropylene. Impact values. So when we're talking polypropylene, you're going to have a lot of different variants of it that are going to vary in impact performance. And so what we do is we can take polypropylene and we can copolymerize it with ethylene monomer, and we can get propylene copolymers. Depending on how much we use and how we do it, we can affect the impact of the material. So propylene as a homopolymer can start with an impact as low as under 1 foot-pounds per inch notched ISOD and get all the way up to no break or plus 10. So we can really vary its performance and impact depending on how much ethylene is in the material and how that's processed. So you can start your homopolymers with low impact, and then the common ones are going to be a 2 ISOD. Though there is a range, you can get a 1.5, you can get a 3.5. 2 ISOD is a very common impact for a copolymer, and then your no breaks, again, which are generally above anywhere from an 8 to a 10. It kind of depends on the supplier and what they will denote as a no break, but really high impact out of your copolymers there. You can also make polypropylene transparent. So random copolymers can also be transparent. I do note though that there is a little bit of haze with your propylene. So depending on the thickness and how it's processed and a few other things, you can affect the haze or cloudiness of it, but you can make a clear propylene. Propylene being semi-crystalline, the clear versions are those that don't follow the rule, that have to be opaque. Propylene is also commonly used for living hinge applications. So think tic-tac things or DVD cases. So where it's built in that it hinges and opens. So very common material for those types of applications. And then another performance feature of propylene that is low surface energy. So if you've ever tried to paint or write on or use an adhesive on your propylene, it can be difficult to get it to stick. If you've ever written on your Tupperware and then throw it in the dishwasher to clean it, your permanent marker's coming off it. Stuff does not want to stick to propylene. So a lot of different variations in your propylenes and different types. And then we can also make them more engineered by filling them with glass or with mineral. That's very commonly done in compounded grades of olefins used for the automotive market. So some applications for propylene, stuff like bottles. So shampoo bottles could be made out of propylene. The syringe bodies that are clear typically are made out of a clarified propylene. Dog bowls, different trim inside of automotive interiors, a lot of different applications in propylene and across varying types as well. All right, so propylene, now we'll talk about ethylene. So you'll notice the chemistry on that. It does not have the additional CH3 off the backbone. And so kind of similar in chemistry, just doesn't have that pendant group CH2 hanging off, CH3 hanging off. And so polyethylene morphology is also semicrystalline, just like your propylene is. A specific gravity range of 0.915 to 965. You'll see when we talk about the different densities, high density, low, linear low on the next slide. That's what is the reason for your large range in specific gravities. Being semicrystalline, it does also shrink quite a bit. So you're in the 1.5 to 2.5 range. Your temperatures, it's still in that 400-ish range, and your mold temperatures in your 70s to 150s. Okay, so some additional information on it. So polyethylenes come in a variety of densities. So you might hear or use high density polyethylene, low density polyethylene, or linear low density polyethylene. That is 100% attributed to if the material is branched or not. So for your high density polyethylenes, there is no branching that occurs. And so that additional monomer is not growing basically off the side and branching out. Your high density ones, as you can imagine, because there's no branching in the way, they can get really close to one another, those different molecules here. So as they're able to get really close to one another, you can pack a lot of that into the same amount of space. So your mass is higher, your volume stays the same. Mass over volume is your density, more mass over the same volume, higher density. So your linear high density polyethylenes, they do not have branching on them. Then if you look at a low density polyethylene, which tends to be a little bit more flexible of a material and have lower density, as the name would suggest, it has branching. That branching stops the chains from getting a lot closer. And so within the same volume, there's not as much mass. And so you have a lower density out of those materials. And then your linear low is kind of a hybrid between the two. You've got much shorter branches that still get in the way a little bit, but not as bad as your full long branches that you get out of your low density. So your ranges for your high density is going to be in the upper 0.93 to 96 range. Your lower densities are in that lower end of the whole range, your 9.1s to 9.2s, and then your linears are kind of somewhere in between. And so you get kind of a little bit in between them. Polyethylene also has low surface energy, just like propylene does. And so your paints, your inks, your adhesives don't really love sticking to polyethylene. It is not as low as propylene, but it does have low surface energy as well. And then another unique product or variant of polyethylene is what is called ultra high molecular weight polyethylene. So made with really high molecular weight, meaning the chains are very, very long. We can utilize that to make a kind of more specialty product. We would not consider it a commodity. It's a more specialized product, but that really high molecular weight allows for excellent wear performance and use in really high end or higher end applications than you would typically see standard polyethylene in. So some of those applications, the ultra high molecular weight polyethylene with that great wear performance and durability is used for iceless rink tiles. So if you've ever gone ice skating, quote unquote ice skating, right? Where they utilize plastic tiles instead of actual ice, that is ultra high molecular weight polyethylene. And then some other applications for more standard polyethylene grades would be stuff like your recycling bins, your milk cartons are made out of high density, some of your chemical containers or gas containers even, will be made out of polyethylene. So common material there as well within a lot of different applications. Okay. And then our last commodity that we're going to talk about today is polystyrene. Again, there are more. There are other commodities, of course. If you have questions about them, feel free to ask, but these will be the three we're going to cover. So now if you look at the chemistry, similar to your ethylene and propylene, but instead of the CH3 that the propylene monomer has, it has a benzene ring off the backbone. That benzene ring gets in the way when it is has a random structure in terms of how it alternates on the backbone. And so polystyrene in general is amorphous. We'll talk about a variant of it on the next slide, but standard polystyrene is an amorphous resin. It is very clear. It has a specific gravity of 1.04. So now we're above 1. So we're no longer materials that will float when they are put into water. They are now higher specific gravity materials. These are going to sink if you were to do it. If you were to take any of those knives, forks, what have you, and put them in the water, they're going to sink. Because it is an amorphous material, it shrinks less, so 0.4 to 0.7 compared to the 2%, which was the general range for your propylene and ethylene as semi-crystalline grades. And we're still in that 400-ish range for melt temperature, and your mold temperatures in the 100 to 160-ish range. Again, always consult the processing for the specific grade you're working with. So some additional information on polystyrene. Polystyrene has excellent clarity as polystyrene. It is also a very brittle product. Polystyrene can also be called, or is also known as general purpose polystyrene. So if you see GPPS, or sometimes people will use the term crystal styrene, they are all referring to standard polystyrene material. Okay, so it's very brittle, but very clear. But what we can do then is we can add stuff to it to improve that brittleness or that impact performance. So high impact polystyrene HIPs, we will take a rubber or impact modifier and we add it to the polystyrene. It improves its impact. So you get a better impact performing product at that time. Because of the rubber though, it does affect the clarity. So standard GPPS is clear, very good clarity. As soon as you add something to it, like the rubber for HIPs, no longer a clear product. So you do lose that. And then a couple specialty versions of polystyrene. Polystyrene can be made to alternate the benzene ring in a, they call it a syndiotactic pattern. So it alternates back and forth which way it is. So if you follow the arrow, it shows alternating on each side. So if you've heard of SPS or syndiotactic polystyrene, those alternating benzene rings allow the chains to get close to one another because they're in such a pattern that now they can kind of get close to one another. And so syndiotactic polystyrene actually will crystallize and is a crystalline version of standard polystyrene. And so it gives a little bit better heat performance, a couple other performance boosts there as well. But heat performance is a big one and it's used a lot more in kind of more electrical type applications. And then also polystyrene can be foamed or expanded. So EPS, expanded polystyrene. And so when they foam it, it can then be used as a nice rigid foam for packaging or insulation or cups, polystyrene, or styrofoam cups can be used for that as well. So a few different variants of polystyrene that are out there for different applications. Okay, if we recall or have them, the younger generation, I'm sure they don't have CD cases, but CD cases, so you think of them, they drop, you step on them, they break, they're brittle. Polystyrene material was typically used for those. Your cutlery that's really fairly easy to break. You go to eat something or maybe use the fork into whatever you're trying to get ready to eat. You push a little too hard and it snaps a little piece of the tongue off. It's probably a polystyrene piece of cutlery. And then your foamed materials. So egg cartons are made with EPS, and some of your insulation or some of the packaging for holding things in place when it ships, stuff like that, also EPS. So different variants of polystyrene and different versions of using it. Okay. All right, then we have some of our engineering products now. So we had our commodities, we did propylene, ethylene, and styrene. Now we're going to talk about some of our engineering products. So now we're moving up a little bit in performance. We're getting a little more complicated. As you can see, the chemistry is a little more complicated than the last three we've had. And so a little more complicated chemistry, but a little bit improvement in certain areas in terms of performance. So ABS is acrylonitrile butadiene styrene. Across the chemistry, that's what you see here. In this section is your acrylonitrile, your butadiene, and your styrene. So you'll notice the styrene, if we remember our chemistry and that these little joints here represent a carbon, this is actually the same then monomer and chemistry of your standard polystyrene. So ABS is made up with styrene being one part of the polymer. ABS is also amorphous, and so it will shrink in the lower range, the 0.4 to 0.7% range. It has a specific gravity it's a little bit on a range because we can have some high impact polystyrenes, or excuse me, ABSs. We can have some high heat ABSs. So depending on the variant or the type of ABS, it will vary our specific gravity. So 1.03 to 1.07 is a good general range to capture most of those ABS grades. And your temperatures still in the 400s, though we are creeping a little bit higher to your 500 range. And then mold temperature still in that 100 to 160 range. Okay. All right, so as you'll notice, as we get into more complex, more engineered products, there's likely to be a little more information on them because there's a little bit more to know about them. So ABS is what we call a TER polymer, TER being 3. So it's got 3 components, A, B, S. And so as a TER polymer, the A in acrylonitrile helps with its heat performance. There are some other smaller things that it also will help with, but the overall driving change when you increase the acrylonitrile amount is going to be the heat performance. Your butadiene, which is a rubber, is good for impact. The styrene portion helps with the processability of the material. So what we can do is we can change the ratio of how much of each of those components is in the ABS grade, and that's what allows us to get varying performance out of ABS. So if you look at some data sheets on a standard general purpose ABS, maybe you're looking at an impact value of a 4, 5, 6 foot-pounds per inch IZOD. Then you have grades that are considered high impact grades that get you into the 8 or 9 foot-pounds per inch notched IZOD performance. And then you have grades that are standard ABS, and then you have high heat ABS grades. So again, I can change out the ratio of how much of each is in it, and that's what gives me my varying performance. Okay. The butadiene rubber in the ABS is what accounts for ABS being an opaque resin. As we mentioned when we reviewed, a lot of amorphous materials tend to be transparent. ABS is not transparent because of the butadiene. It does not allow the light through. ABS is a very tough, we'll call it a tough material. The butadiene really helps with its impact performance, but it also helps with impact performance at room temperature and low temperature impact. So when we get into materials like the polycarbonate later on, its room temperature performance is excellent. Low temperature is not as great, unlike ABS, where it does have pretty good low temperature impact performance. But the butadiene also accounts for ABS's poor UV performance. If you've heard it once, hopefully you hear it a few more times. ABS is not a great material to be used outside. It yellows very quickly. If you see the little picture we have of a part, you can see around the batteries, the color was normally, or what it started as, so more of a tannish beige-ish color, and you can see it discolored greatly into this really nasty yellowish color. And so that was getting hit with filtered light, filtered UV light, and so it attacked the ABS and caused it to shift colors. That's going to happen with ABS anywhere, really, if it's outside or seeing filtered light. So we will always recommend ABS is not used outdoors. I do not have a slide, or I do not talk about ASA, but that could potentially be the direction that you would go if you need something that's kind of similar to ABS, but you do need UV performance. So again, I don't have any slides on it, but that would be the next one that we could, or that could be talked about. Then lastly, MABS, which stands for methyl methacrylate ABS. Sometimes it's just typically called transparent ABS. They don't always give MABS as the chemistry. They'll just call it transparent ABS. What happens is they'll change the matrix. So instead of just an SA matrix, so styrene acrylonitrile matrix, they also add in then methyl methacrylate. So the matrix the butadiene is in changes its refractive index, and now the two match. And so it allows light through. So really complicated way to just say, we can make ABS transparent. We just alter the matrix the butadiene is in. So there are transparent grades of ABS. Okay, so some applications, think housings, think things that have to have good dimensional stability. So maybe components on hospital beds, maybe housings on medical machines. The little window on your soap dispenser, that a lot of times they use MABS for that, transparent ABS. Maybe the push handle there itself is ABS, and then the lens itself is MABS, transparent ABS. ABS is used a lot in pipes and fittings. And then it's also used a lot for automotive. If you've got little trim parts or little like decorative parts, specifically your really shiny parts, a lot of times tend to be ABS, or other variant parts within a car can be made out of ABS. And then the big one that we always like to point out is Legos are made out of ABS. And so good dimensional stability, we need to be able to put the parts together, right? Okay. All right, so ABS, now we're talking about polycarbonate. So moving on our list of engineering products. So polycarbonate is also an amorphous material, but it is clear. So amorphous grade that is clear. You'll see the specific gravity of this material jumps quite a bit. So we had been in the 1 to less than 1 range. Polycarbonate jumps up to 1.2. Shrinkage is still in that low range, so 0.5 to 0.7 for polycarbonate, amorphous material again. Now our temperatures are starting to creep up. We're in the 500 to almost 600 degrees, so a little bit hotter of a material, a little bit warmer temperatures for it. And then mold temperatures in the 150 to 250. Again, a wide range because I'm trying to cover generically where some of the other polycarbonates may fall. And so what you'll see now too, and what I want to point out is our 2 benzene rings here in this chemistry with your CH3 groups. This is the remnants of bisphenol A. So we will talk about it in the next slide, but I want you to, if you can, keep in mind what this looks like. There is another material that contains it as well that will be pointed out when we get to it. Okay, so again, as we're getting a little more specialized, there's a few extra words on these materials because they do a few different extra special things. And so I want to point them out. So polycarbonate, excellent toughness, great impact performance when we talk about unmodified materials. So 10 plus foot-pounds per inch IZOD out of a standard polycarbonate, as long as we're not getting too small of a radius or too thick of a part, which we'll talk about in a little bit, but excellent toughness out of polycarbonate. Polycarbonate can also be formulated to utilize a UV stabilizer and maintain clarity. So a lot of times when you start adding stuff to clear materials, you start losing the clarity because you have something else that's competing with allowing the light through. So polycarbonate can be formulated with UV stabilizers and then maintain its clarity. BPA, as it should be talked about because it is a part of polycarbonate and we get asked about it. BPA is part of the chemistry. So we react phosgene and bisphenol A to make polycarbonate. So if you have an end user or you are an end user and you want to be able to market that the material has no BPA, you're not able to do that with polycarbonate. Polycarbonate is made with BPA. It is there. The one thing though I do want to point out is that based on safe harbor levels or levels that have been established by EPA or also the EFSA, which is the European safety standard, they have set a safe level at 0.05 milligrams per kilogram of body weight. So, which means nothing if you don't know the exposure of the material that you're seeing. So with polycarbonate, with the exposure level that you will have to bisphenol A based on products made of polycarbonate, you would have to come in contact with or eat or drink food or beverages that come in contact with polycarbonate at an excess of 10 times your body weight to even get to that exposure level. So BPA is a concern, as with anything really, it can be, in very high levels. So polycarbonate has BPA, but the exposure to it is very, very low, that it would be very difficult, hopefully impossible, hopefully we're not eating or drinking 10 times our body weight, to reach that threshold for exposure to the polycarbonate, the BPA in polycarbonate. So just wanted to point that out. Obviously it's a thing. I'm sure questions will surround that, but it has to be talked about, right? Okay, so polycarbonate, excellent impact. There are some nuances to that. Polycarbonate is also a very notch sensitive material. So if I use a different radii, a different thinner radii, it will affect how the performance will be for the polycarbonate. So meaning in a practical sense, if I design a part with really sharp corners, so there's almost no radius on it, it's not going to perform at the impact level you would expect out of a polycarbonate, you're going to drastically decrease its impact. So if I design, just as a simple application to think of, a tray out of polycarbonate, and I don't round the corners, I just make them very sharp corners. If I drop that tray, being that it's polycarbonate, I might assume that it would be fine and it wouldn't have a problem dealing with that level of impact. But those sharp corners are likely to crack and break and not show the impact performance you would expect out of standard polycarbonate because it is not sensitive. Polycarbonate also has what's called a critical thickness, where if you get it too thick or design a part too thick, you also then lose impact value. So for polycarbonate, that value is right around 5.5 to 6-ish millimeter thick. And once you get to that, you lose all of your impact value. So if you follow the arrow that's kind of pointing over, you can see impact performance depending on the temperature range. But if you're at room temperature at your 73C, you're up around the 18 impact, foot-pounds per inch impact. So excellent impact. You hit that critical thickness and you drop all the way down to about a 3 impact. So again, on paper, you look at a polycarbonate, it's got excellent impact. You're like, that's what I want. That's what I need to do. I'm designing around that. I want that performance. But if a part is designed with a sharp corner, sharp edge, or it is designed too thick, it is not going to perform the way we expect it to. Okay. And then lastly, some other variants of polycarbonate. Blends is a common thing that is done with polycarbonate. So you might blend it with a PBT because you want to improve the chemical resistance of polycarbonate. Polycarbonate by itself, really not great chemical resistance. So maybe we blend it with a PBT to improve that. It also is sometimes blended with ABS to improve its low temperature impact. As we mentioned, ABS, because of the butadiene, good low temperature impact. So I blend it with PC to get a PC ABS with good low temperature impact and better impact at low temperature compared to a straight polycarbonate. Okay. And then lastly, polycarbonate can also and is commonly copolymerized with other monomers to do things like improve low temperature impact. So can be copolymerized with something like a siloxane. It can be copolymerized to improve UV performance. It can be copolymerized to improve heat performance and chemical resistance performance. So a lot of different variations of PC copolymers that exist to help with performance in those key features as well. Okay, and some applications for polycarbonate, again, great impact. So stuff like your automotive lenses, if you've got rocks that are coming up and hitting the polycarbonate can withstand that impact. They tend to be coated generally to help with scratch resistance also. That's a little side note on that, but because of being able to withstand the impact of rocks or other things that might come up from the road, lenses are typically polycarbonate. A lot of meter housings and stuff where it needs to, we want to, maybe not allow someone to crack it and break it open and get to whatever's behind it, but then still be able to see through it, maybe even protect it from UV if it's a UV stable grade and make sure that the UV light doesn't get through it to what's behind it. Safety glasses are commonly made out of polycarbonate. And then those really large water jugs generally are also made out of polycarbonate. If you were to use a material that was a little more brittle and you dropped one of those things that are full with lots of water, be very heavy, likely to crack and break, and we can't have that happening. So a lot of good options to utilize the really good performance in toughness that polycarbonate has. Okay. All right. Now, nylon, as I mentioned again, there is a separate presentation just going over all the a bunch of different types of nylon. And so in this case, I kind of did more of a covering of the family of polyamide versus each individual material a bunch of times. So I gave a general performance review and then the ranges that kind of go across the majority of those nylons as well. So the morphology of nylon is going to be semi-crystalline. You can make amorphous nylon. So they do have amorphous nylons that are clear. Or microcrystalline nylons that are also then clear. So that goes against the standard semi-crystalline materials are, opaque. And so, but our standard nylons that we'll be talking about, they're semi-crystalline. Specific gravity ranges from 1.01 in your long chain grades up to your 1.18 in your short chain grades, so more like a 4.6. And then your shrinkage also varying range because we're talking a bunch of different materials at once. So 0.6 to 2.2, depending on which nylon material type we're talking about. Mold temperature, again, and melt temperature, big range because The longer chain ones are processed and ran at lower temperatures, so more in the 390, 400-ish range, all the way up to your high temperature ones like a 4.6 that are going to be more in your 500-600 degree range. So a big range here. And then I included your chemistry for two common ones that I would imagine we're most familiar with. So polyamide 6,6 and 6, but I also included within those range 4, 6, and 12 are included in those ranges as well. Okay. All right, so some information about nylon in general. The standard nylons that we're talking about right now are considered linear. So there's no benzene rings, there's no aromatic content to it. They're just what we call standard linear grades. And so your 6, 6, 12, 10, you name the number, as long as it's just a number, is going to be a linear nylon. There are specialty grades of nylon that I am not covering in this presentation, but there are specialty nylon materials like PPA or PARA that are going to have aromatic content. So they're going to have benzene rings in their chemistry. Those are specialized. Again, not talking about them here, but if you have questions about them, feel free to let us know. Your 4,6, 6, and 6,6 materials are going to be your standard nylons that are considered short chain nylons, or we just call them nylons. And then long chain polyamides, LCPA, if you've seen that acronym, that would refer to your nylons like your 10s, your 12s, your 9s even that are kind of odd. But those longer chain, higher number nylons, those are within the long chain polyamide portion of family. Okay. So nylon, though, in general, great chemical resistance, specifically to automotive oils and greases. So great for automotive applications because it has really good chemical resistance to a lot of the chemicals it might come in contact with in an automotive application. Nylon also has really great wear performance. In terms of lower speeds and velocities, it's not quite as good as acetal on metal, but it is way better than acetal if nylon is wearing on itself. So resin on resin wear, nylon takes the win there compared to acetal materials. And then different nylon materials also have different performances for wear. So something like a 4,6 has improved wear performance because it's a more crystalline polymer than your 6 or 6,6 would. Okay. Moisture sensitivity. Nylons pick up moisture. So it is an issue for nylon if they pick up a ton of moisture. Like any other hygroscopic material, it can be a problem. So I didn't mention it as readily, but your ABS is going to pick up moisture. Your polycarbonate materials are going to pick up moisture. It just tends to be quite an issue with nylon. So I figured this was the time to bring that up. So issues with moisture absorption, your shorter chain nylons absorb more moisture than your longer chain ones do. So your 4,6, your 6, your 6,6 are more likely to have issues with moisture absorption or maybe not being dried properly than your long chain nylons are going to. So 6,6 going to pick up more moisture than a 12. So we have to be a little more cognizant of it when we go to run those materials and make sure we're drying them correctly. Okay. Another big variant or change that you can make or do with nylon is it is common to impact modify nylon materials. So you might hear the term impact modified, meaning I add an impact modifier to it, which again, those are rubber in nature. Or you might hear the term toughened or super tough grades. And so those all mean relatively the same thing. I'm adding impact modifier at varying levels to improve my impact performance of the material, the nylon itself. Okay, so standard nylon without impact modification is, I wouldn't necessarily call it great or the best with impact, but as soon as you add varying levels of impact modification, you can get really good impact out of the nylon materials. Another common thing that we'll do with nylon is we'll add heat stabilizers. So in the case of maybe we're using it for under the hood applications and it's going to see, maybe it's elevated temperature for a long period of time, or at least want to test it for a long period of time as a safety factor, we can go through and heat stabilize these grades so they can withstand those temperatures for an extended period of time. The one thing though that I like to point out and keep in mind is that standard heat stabilizers for nylon are copper based. Okay, so copper, it tends to make the material a little more green in coloring. So if you are color matching something and you were using a non-copper heat stabilized material and you're switching to a copper heat stabilized material, you're going to see a variance in color. It's going to look different. Or if you just want to have it a very specific color every time, you're going to have variation in the green hue of each lot. So you have to fight that as well. There are other heat stabilizers that do exist that are non-copper based that do not affect the coloring as much as copper-based ones do, but they're not as effective. So you're not able to withstand as high a temperatures as you can with the copper heat stabilized grades. Okay, and then just some pictures to kind of show what that looks like. I don't have as good of pictures as I would like on it to really show off, but you can see in these pictures off to the left, you can see that there's a discoloration there. So all the way here on the left, you've got a heat stabilized and impact modified. This would be a super tough grade. So you can see it's a little bit deeper in color versus a more whitish color of the non-heat stabilized version. And then here we have a standard 6. We have a non-heat stabilized, or excuse me, a non-copper heat stabilized 6, and then a copper heat stabilized 6. So you can see as it goes down, it changes and gets a little deeper in color, a little more discoloration from it. So all things I like to point out as well. So we're aware that that is what happens, and it's pretty standard for using heat stabilizers in nylon. So it's worth noting. Okay. Some applications, very wide range of applications because we have a broad range of nylons that we were talking about. Again, tried to shorten it down as best I could, but stuff like your under the hood applications, radiator end tanks, stuff like that under the hood are going to be nylon materials typically. Zip ties are generally going to be nylon based. Modular belting, so again, I mentioned resin on resin wear, much better with nylon than acetal. So a lot of modular belting then, plastic modular belting could be not a nylon of some sort. And then gears and stuff like some of your blenders or the creamy or what have you, if they're running really quickly and have to wear really well, a lot of times they'll use something like a 4-6 for high speed, high pressure, or even maybe slightly high temperature. If it's running really fast and the temperatures get high, you might use a 4-6 for gears. You could use a 6-6 for gears and stuff like that, but those would be used in those applications as well. And even maybe some of the housings and stuff could also be nylon as well. So a lot of options for nylon applications. Okay. All right, and then we have, I believe the last engineering product we're going to cover is polyesters. And so PET and PBTs. And so we'll cover them kind of as a two-part family, if you will. Both of them tend to be semicrystalline, though there is an amorphous version of PET we'll talk about briefly, but semicrystalline in nature, specific gravity between 1.3 to 1.4, kind of depending on which one it is, if it's a PET or PBT. Your shrinkage is between 1 and 2%, again, depending on which one you're looking at, but they are semicrystalline, so you do see a larger value for shrinkage. And then your temperatures are in the 500-ish range, and your mold temperatures are in the 1 to 200-ish range. Okay. So the difference here between your PET and your PBT is that your PBT has 2 additional CH2 groups on the backbone. So 2 additional CH2 groups. That's the only difference there. But it does, because of those 2 additional groups, it makes it a longer chain for the PBT, and it makes it a little bit more mobile. It's easier to move. And so you'll see how that comes into play on the next slide a little bit. So some performance differences. So PET, once it's been optimally crystallized, so we take the time to make sure it crystallizes appropriately when we process it. PET can be a pain to crystallize, but if it meets its optimal amount, it will outperform PBT with temperature and stiffness. So that you can see down here in the graph, you can see PET starts with a higher stiffness, maintains that, and then doesn't start losing it until a little bit higher temperature than the PBT. So a little bit better stiffness and a little bit better temperature performance if you optimize the crystallinity in your PET. Okay. But PBT, because of those additional CH2 groups, it's more mobile. It moves a little easier. It crystallizes easier and faster. Generally speaking, if you're going to do injection molding PET grades, they're generally either filled or have some nucleating agent or some type of filler to help aid in the crystallization, because it does not want to crystallize very quickly when you're using a PET. There are also 3 kind of general groupings of PET. The first one's going to be your crystalline PET. So as would be what you see in the chart here, one that we take the time to crystallize fully. Sometimes it'll be referred to as an engineering PET, so used for more wear applications and applications that are going to utilize its crystalline structure for performance. Then you have amorphous PET grades. Sometimes they'll be referred to as bottle grade PETs. And so these are ones where we're going to, when we process it, we're going to freeze it quickly so it doesn't allow it to crystallize. So you effectively make an amorphous version of it. And so that's what you're going to get out of kind of your bottle type PET grades. And then there's also copolymers. So if we take PET and we copolymerize it with glycol, you get a material like PETG. And so if you've seen those materials floating around, that's a variant of PET. It's been copolymerized. So PET for bottles, again, we stop it from being able to crystallize. And it doesn't want to crystallize quickly either, but we make effectively an amorphous or bottle grade version of PET. But it also, PET has excellent performance in terms of low permeation of oxygen and CO2. So it makes it for a really good material to have alcohol. It's also resistant to alcohol, and carbonated beverages. So it's not letting the carbonation out. So it makes it for a good material to be used for those types of beverage containers. And then PBT, because it does crystallize faster, it's more mobile, it's able to get into its crystalline structure quicker. It's more common to use for injection molding than PET would be. And it also is more suited for having impact modification because PBT is already a more flexible material to start with, a little bit better impact. So then we can improve upon that further by adding impact modification. So you'll get impact modified PBT grades, no problem. And so a little bit better impact performance than your PET will give you. Okay, so some common applications for these materials. Your keyboard housings going to be PBT, your bottles, PET, blister packaging for, you name it, medical, toys, whatever it may be. A lot of times we'll utilize PET. And then connectors, different electrical applications, going to utilize PBT pretty commonly. Okay. All right, so now we're going to get into the specialty products. You'll notice there's a lot of interesting value propositions about them. LCP that I'm going to speak about briefly. This is the only slide I have on it because these aren't materials that you are necessarily running into in large quantities or applications that require these types of materials. So I'll go over them, but the majority of the time we're not seeing these types of materials out there and these types of applications for them. So, but it is good to know about them and kind of know how they perform. So LCP, liquid crystal polymer or liquid crystalline polymer. I've heard it both ways. Its morphology is neither semicrystalline or amorphous. So semicrystalline materials having their crystal structure, when they are processed and they're in the molten state, they do not have any crystallinity left to them. So they're all amorphous when it's molten down. That's why when it shrinks and it tries to get back to its crystal structure, that's when your crystallinity starts back up. LCP, on the other hand, they have sections that remain crystalline even at the molten state. So it maintains its crystal structure in those areas. And so it kind of has its own morphology. It doesn't really fall into one or the other. You'll notice that there's a lot of ranges here. The reason for that is that LCP, it's more of a family of polymers versus one distinct chemistry. So you can utilize different backbones that the LCP sections are grafted off of. And so because of that, you'll then get a varying range of performances for LCP. So you'll see specific gravity ranges from 1.2 to 1.8. Your shrinkage is lower for these materials. Typically, you generally have a lower shrinkage from them. Your heat can be anywhere from middle fives up to almost 700, again, depending on the backbone that's being used, because that will help dictate how you're going to process it. And then your mold temperatures from mid 100s to almost 300 degrees, again, depending on the backbone. Some value prop or the reason you would use something like an LCP is it has excellent flow capabilities. So you're able to fill thinner parts than you would be able to with other standard products. Really, really great flow performance. It is also inherently self-extinguishing. So you don't have to add anything to it. You do not need to give it a flame package. It will inherently self-extinguish. And so it would achieve a V0 5VA rating through UL without anything needing to be added. Has excellent chemical resistance and good, really high temperature resistance. So stuff like if I'm going to make a circuit board, so it's going to fill something really thin, but then also needs to be soldered, which is a high temperature process. It can withstand that as well. So it's used a lot for circuit boards, LCP is. And then the one thing which I didn't put in here would be its one negative or downfall would be that it does not have great weld line strength. So if you've ran it or have experienced it, that's the one of the downsides for LCP. Okay, and then I have two more specialties and then a quick one on TPE. I realize that we're getting into almost an hour worth of me talking, and that can be a lot, but just a lot of good materials to cover. So I apologize for that, but we'll keep trucking. So now we're talking about additional specialties. We're talking about PEEK, so polyether ether ketone. Its morphology is going to be semicrystalline, specific gravity of 1.3, a little bit higher shrinkage, so about 1%. For shrinkage because it's a semicrystalline material. And now we're getting into some pretty high temperature products. So we're in the 700 range for our melt temperature, comparing that all the way back to our commodities that were in the 400. So you can see the big difference in our temperature performance, right? And then our mold temperatures are also very hot. So we're in the almost 400 degrees Fahrenheit for mold temperatures for polyether ketone, ether ketone, excuse me. Some performance features about PEEK and why you might use it. Excellent chemical resistance. Semicrystalline material, they tend to have excellent chemical resistance. PEEK is no exception to that. It has only one known solvent at room temperature, and that's highly concentrated sulfuric acid, meaning that only one chemical is going to dissolve down PEEK at room temperature, and that's sulfuric acid. So all the other really aggressive chemicals and stuff like that, they do not dissolve down PEEK at room temperature. PEEK maintains good chemical resistance to a lot of different chemicals up to almost 400 degrees F. So sometimes when you're thinking chemical resistance, you also have to think in environment exposure temp. So if it's something where it's going to see those chemicals, but at a high temperature, we also need to take that into account because it needs to, one, withstand the temperature and then also withstand being degraded by the chemical at that temperature. So PEEK can do that, really high temperature performance and good chemical resistance at high temperatures. Tribological performance, so wear performance, again, kind of like we talked about for nylon. PEEK has excellent wear performance. Without lubricants added, it has low COF values. And so on the little chart there, you can see a few different values for different materials that are used in wear applications. And you can see PEEK's kind of right in line there, real good performance. The one thing that's nice about PEEK or an advantage to PEEK would be that it has really high limiting PV values. So limiting pressure velocity values. So wear performance also can be dictated by how much pressure you put on when it's wearing on whatever it's wearing on and how fast you're trying to get it to move. And so the higher the value, the more it's withstanding that and is going to be okay to be ran at high pressures and high velocities. So if you're looking at the slower speeds, the 10 to 100 foot per minute, range, you're in the 40K limiting PV. And then when you get to the 1,000 feet per minute, so you're really kind of booking it, you're at over 20K still. And so to give a value to compare that to a different material, your acetal is in between the 5 to 20K across the ranges. So outperforming that if you're looking at using something with high speeds and pressures. And then also temperatures as well. So higher temperature performance as well out of the PEEK. So good wear performance, high temperatures. Okay. Heat performance. Continuous use around 460 degrees F. It's one of the highest commercially available semicrystalline grades for thermal performance. And then also it is self-extinguishing like LCP. It has an LOI of over 35%, meaning I need more than 35% oxygen for it to continue to burn. So great self-extinguishing performance without flame packages needed and good temperature performance. It makes it good for applications in aerospace. So it is used in aerospace applications as well. So some main applications might be some propellers, maybe some plastic screws that might be utilized for some light weighting in aerospace, different connectors. I understand those pictures of connectors aren't necessarily PEEK, but to give an idea that they are used in connectors. PEEK is used for high temperature connector applications as well. Okay. And then our last specialty polymer we're going to talk about is PEI. You'll notice maybe some of the other specialty ones that I didn't talk about. I didn't necessarily go into a PAI. I didn't talk about sulfones. Again, if you have questions, feel free to reach out. I'd be happy to help. So PEI is an amorphous resin now. So unlike PEEK, that's semicrystalline, PEI is amorphous. It is also clear. It is amber in color, but it is clear. You can see through it. So that could be an advantage depending on what you're trying to do with your application. Specific gravity of 1.27, low shrinkage. Again, it is an amorphous resin, so 0.5 to 0.7%, and still high temperatures as well. So melt temperatures in the 700 range, just like your PEEK. We're getting into high temperature performance. And then your mold temperatures around 300 degrees F. So as I mentioned, if we recall or remember when we were looking at the polycarbonate, we remember this structure right here. This right here is BPA. It is also present in PEI. Now, PEI being such a high-end material has a few less applications that we can put it into, but it does have BPA. So if that's a requirement to not have BPA in the product, PEI does have it. It could be a downside. All right, so some performance features, high temperature performance. As you can see with the high temperature needed to process it, it has really good heat resistance. So its TG is 217C or about 422F, and it's going to maintain a lot of that stiffness performance out until that temperature. So if you look at the chart, you can see it loses some a little bit, but really it holds on to most of its flex performance, flex modulus, out until right about its TG, and then it loses its performance. So good continuous use performance, we'd call it to about 190, 200 degrees C. So great temperature performance there. Good dimensional control, so it can hold tight tolerances. By nature, being an amorphous material, it doesn't shrink a lot to begin with, but it can also maintain its tight tolerances for a long period of time and under load, and also at elevated temperature. So because it's a high temperature material, it's withstanding those high temperatures and maintaining its tight tolerancing across that. PEI unfilled also has some of the highest stiffness and strength performance compared to other high temperature amorphous materials. So if you need a good unfilled high stiffness material, PEI is that material for you. And then lastly, its big thing that's utilized pretty commonly for applications is going to be what we call FST, flame, smoke, and toxicity. So in the aerospace applications, we care about flame spread. We want to make sure that it doesn't continue to burn for a long period of time, or really at all if we can help it. PEI has an LOI of 47. So PEEK was self-extinguishing at 35. PEI is also self-extinguishing, but at 47. So you need quite a bit of oxygen, about double what we have in our standard air before it will continue to burn. So it's self-extinguishing. It meets those flame spread requirements. It also is good for heat spread and smoke density and toxicity. So that's what the smoke and toxicity is. If it starts to burn, we want to make sure that any smoke that is given off is not very dense and we can still see through it. So stuff like we don't want it to burn. We want to make sure people can still see. We also don't want it to be toxic. So if something's burning and it's giving off smoke, we don't really want it to be a danger to the people that it may come in contact with. So because it performs well in those three categories, flame, smoke, and toxicity, it's used pretty heavily in aerospace applications as well. Okay, so some applications, a lot of different aerospace components. It was hard to find pictures of diving deep down into those specific applications. So picture of a plane, a lot of aerospace applications. Oddly, it's used for guitar picks too. It has the right sound for being used as guitar picks. So that's one of those unique applications that it has. And that's also used for components in 5G antennas and other type of antenna products. So it's used commonly there as well. And a lot of other applications also, but to give a few examples. Okay. And then lastly to cover, I've just got a couple slides to go over TPEs. Again, it's very brief. There is an entire presentation on it if you'd like to go see it, but it's just a real brief overview of the standard and common TPEs that we're going to see. So most of your TPEs are going to be semicrystalline. It depends on what you want to shove under the TPE name. If you want to look at PVCs and kind of consider them more elastomeric, your flexible ones, they're going to be amorphous. So that's why I have most instead of all. Your specific gravity ranges from 0.9 to 1.3, depending again on which TPE we're looking at. Shrinkage from 0.8 to 2.5. And then you can see a decent range for your mold temperatures, 380 to almost 500, and mold temperatures from 60 to 160. So TPE as a term, thermoplastic elastomers, can be used as a term to denote a family of polymers then that will have a hard and soft segment. Unlike standard elastomers though, thermoplastic elastomers can be processed on standard thermoplastic equipment. So I can injection mold it, I can extrude it just like I would another hard plastic. And so that's where this comes in. And then the different segments that are used, the hard and soft segments, that's going to dictate its performance. Okay. So TPEs. So if I want a styrenic based TPE, or what some people just generally call a TPE, to not get confused with the family name TPE that all of these fall under, I call it a TPES or a styrenic based TPE. Whatever works for you, that's I just do it, so it's a little bit easier to keep track of which type of TPE we're talking about. Styrenic based TPEs are typically styrenic based soft segment, so an SBS, SIS type soft segment, generally in a propylene hard segment. Really good wide range of hardnesses, so from double zero A's all the way up to 100A. Generally, then we start getting into the D range, but good low cost option. So if I need something, I'm going to overmold something and I just need a nice soft touch feel, TPE is a great option for that. Great colorability, great overmolding capabilities. Because of the propylene hard segment, it wants to inherently overmold to propylene and ethylene, but you can make and formulate grades that are specially made to overmold onto other materials. ABSs, PCs, nylons, they can be made to do that as well. The service temperature of TPEs, styrenic based ones, will be limited to the propylene hard segment. So continuous use around 200-ish F, because again, you're limited by the propylene. TPVs, that stands for thermoplastic vulcanizate. It goes through an intense mixing process, the vulcanization process. It forces the soft segments to cross-link. Because of that cross-linking, it acts a little more rubber-like. So you get a little bit better compression set performance, a little bit better tear strength performance than you would out of a standard styrenic-based TPE that's not been cross-linked. Most of the time, TPV grades are going to be EPDM and propylene hard segment, though there are some styrenic soft segment grades that exist. So they would then vulcanize the styrenic rubber instead of EPDM. Good wide range, not as wide of a range as styrenic TPEs, but still a decent range of hardnesses available. My service temperature is still going to be limited by the propylene, so I don't see a huge improvement necessarily in terms of continuous use temperature. You will see an improvement in compression set though, and the resilience because of the cross-linking. The other thing to note is the vulcanization process, because it will utilize a catalyst. A standard catalyst, if it's using a phenol type, will result in some small black specks in a natural TPV. So that is a normal occurrence. All the suppliers try to limit how much it happens, but that is a normal occurrence out of TPVs. They do have special grades of TPVs that utilize a different catalyst, so you don't have that problem. But just note, if you're getting just a standard grade of TPV and it's natural and there's a little black speck here or there, that's normal. That's going to happen. Okay, then we have TPU, so our standard aromatic TPUs. So when we think kind of just a general thermoplastic TPU that we're going to run, they're aromatic in nature. There are also aliphatic grades that are unique and a little different, but your standard TPU grades that you see on the market are going to be aromatic. They're based on typically either ester, ether, or capropolyols, and then utilizing slightly different diisocyanates. So TPU though in general, a little bit on the higher end for hardness range. It doesn't get as soft as TPVs or TPESs, but it does exhibit excellent abrasive wear. So if you got stuff that maybe it's downhole in oil and it's going to be hit with sand and stuff running through it, it's going to resist that abrasive wear of that sand trying to hit it or wear on it or what have you. Excellent abrasive wear out of TPU. A little bit higher temperature performance compared to TPE and TPVs. And it also inherently wants to overmold or can overmold onto some polar substrates like nylon and ABS. It does not, though, want to overmold onto propylene and ethylene. So when you go to overmold these materials, they are opposite. So if it wants to overmold onto a non-polar propylene or ethylene, unless you formulate it differently, it does not also want to overmold onto polar substrates like nylons or ABSs or polycarbonates. So just keep that in mind. And then lastly, TPC, which are going to be your copolyester elastomers. Sometimes supplier will use the acronym COPE instead of TPC. They exhibit excellent chemical resistance, great low temperature ductility, and then you have special grades that can withstand higher temperatures than some of our other materials, so up to 340 degrees F. So of our TPEs, it's kind of some of the highest temperature performing options we would have available to us. TPCs are also on the higher end of the hardness range. So you're not going to get into those low hardnesses that you can get with the other materials. And then it also costs. So you get the better temperature performance, a little bit better chemical resistance, low temperature ductility. You're going to pay for it a little bit. And it also would like to overmold onto polar substrates like ABS and polycarbonate materials inherently. Okay. And so some just general applications for TPEs overall: caster wheels, hydraulic hoses, butt stocks on guns where it's the nice soft kind of padding, and then any type of overmold for like a nice feel on a screwdriver or maybe on your drill for an ergonomic handle that you can tell is kind of more of a rubbery thermoplastic elastomer type product. That's where your TPEs are going to fit, so they can help with that. Okay. And with that, I apologize. I went longer than I normally do, but there was a lot to cover. So with that, that is what I have for you guys today.
Awesome. Thank you, Andrea, again for your comprehensive presentation. At this time, if you have any questions, please type them into the questions section or raise your hand and I will unmute your microphone. It looks like we do have some questions up there. We do have Jason Merkel, our technical manager, on hand today to assist Andrea with some questions. As a reminder, as you type your questions, please remember to complete the survey at the end of this webinar. If you're attending live, that is, your responses will help shape future Chase the Knowledge webinars, and we welcome your feedback. Also, please be sure to check out our webinars page at chaseplastics.com/webinars for past webinar recordings and future webinar announcements and registration. If you'd like to have a custom Chase the Knowledge topic presented to your organization, please reach out to Andrea or myself and we can get that set up for you. So Jason, I'll hand it over to you. It looks like we got some questions in the bar there.
Sounds good. Thanks, Sherry. Andrea, your first question is, I believe this is going back to the polypropylene section. Does clarifier for clarified polypropylene affect the surface energy or affinity for things to stick to the surface of polypropylene? The example given is like food containers that may stain. Would clarifier have an effect on that?
Not that I'm aware of. I think the overall propylene is the one with the lower surface energy. Maybe if it acts a little bit like a nucleator in the sense that it provides those areas for it. A lot of times if you get a harder surface because it crystallizes more at the surface, you end up with it even less likely for things to stick to it. But overall propylene in general just really does not have it has really low surface energy regardless. So I don't know the effect, nor do I have data on it, but maybe slightly, again, not enough to where it's still low surface. Nothing really wants to stick to it.
Yeah, I would agree with you. Given that it affects some of the crystallinity, there might be a slight change, but I wouldn't expect it to be worlds apart from standard propylene. Next question is, what is the benefit or effect of short versus long chain nylons?
Sure. So in that case, we would be comparing the different nylons. So stuff like, we would say a 6/6 would be, for this example, we'll use as the short chain nylon. So your 6/6 compared to a 12. So they're going to perform a little differently based on the interaction of their chemistries and the additional carbons in the long chain. So your shorter chain materials are going to have a little bit higher temperature performance, a little bit better wear performance typically, and they're going to pick up a little bit more moisture. Whereas your long chain materials, they're going to be a little more flexible because the chains are a little more mobile. So you get a little bit better flexibility out of them. They pick up less moisture and they're not as heat resistant as other nylons, as the short chain nylons. So, and there's the whole reason why behind that is going to be your hydrogen bonding, which I go into quite a bit of detail in the nylon presentation. So I would highly encourage, if you wanted more information on that, to check that one out. And just send a note if you want us to send you the PDF version of it to read through. But it does change your performance based on if it's a long chain or short chain.
Wonderful. Next question is, do we have a webinar that helps molding technicians understand materials and how to adjust processes based on the material and their respective additives?
We don't. The next presentation will be on additives, so we will likely talk briefly about how it could affect and what changes would need to be made. So for instance, adding like a flame package, you would have to generally half your residence time for the material and how that affects it. And so we don't have a webinar on that. And I would say if there are specific materials in mind that we're curious about or need information on, to let us know, and we can certainly get those specific examples given, because there will be slight adjustments to different things, whether you are blending it, whether you're adding glass, whether you're adding certain additives. There could be some adjustments that are made when you process, and so to know that up front would be ideal.
Wonderful. Next question is asking about seminars specifically on nylon, when there is one. This particular contact mentioned that they run a lot of different styles of nylon. I believe that may be existing already.
Yeah, it is. Yep. So that was understanding polyamides. It's a little bit older. I want to say maybe we did it 2 years ago. But it exists and it's out there. So certainly just send a note and just say, hey, can I get that, or the PDF, and we'd be happy to share that, because it goes over the chemistry, it goes over the naming of nylon, and then it goes over the hydrogen bonding and how that affects the different nylons in terms of heat performance, moisture absorption, stuff like that.
Yeah, Andrea, we did understanding polyamides back in March of last year, so they can find that recording either on our webinars page or on the YouTube channel.
Perfect, thank you.
Thanks, Sherry. All right, Andrea, what appears to be the last question. Can TPVs be used as an overmold and stick to the substrate?
Yes, so being that they are propylene, like standard styrenic-based TPEs, the propylene hard segment will bond to propylene and ethylene. There are some grades that exist that have been specially formulated to overmold onto other materials. Generally though, for those overmolding materials, it's a TPE, not a TPV base, but standard TPV will overmold to propylene and ethylene.
All right, I think that wraps up our question section.
All right, well, we would like to thank all of you for taking time out of your busy schedules to attend this Chase to Knowledge webinar. We hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. Her information is posted on your screen. Thank you all for attending, and we hope to see you at our next Chase to Knowledge webinar in December.